friends. Welcome to our rotational notes 4.3. Again, the party starts off with a little GeoGebra, and we'll walk through that after we get dilations. Well, let's get into the book stuff. So we're going to be performing some rotations, compositions, and rotational symmetry. So 3 things on the docket today. First off, the definition. A rotation is indeed a transformation in which a figure is turned about a fixed point called the center of rotation. And the angle with which we are going to rotate, we're going to keep it simple, my friends, right here, 90, 180, and 270. So 3 things that you have to memorize from this section, how to perform rotations whenever we are rotating around the origin, either 90, 180, or 270 degrees. So we have it here in variable form. Let me just give you a numerical example. So for instance, say I'm at this point 2, 3 in the first quadrant, and I want to rotate it 90 degrees. Well, the rule says, I'm looking here, we want to switch the coordinates and we want to negate the x value. All right, so let's do it. So flipping the coordinates would be 3, 2, and then negate the x value, the new x value, I should say. So now we are -3, +2. And that's a 90-degree rotation. As you can see, the x value is going to switch from being positive to negative if you go 1 quadrant over in a 90-degree fashion. All right? Now, if I'm flipping this thing 180, that is going to take me down here. The rule tells me to negate each value and keep the order the same. So that 2, 3 is going to turn now into -2, -3. And that's going to be in your third quadrant. So positive, positive in the first 2 are going to be negative, negative when you switch 180 degrees rotation. And then 270 is going to take you 3 quadrants away. So it's like you're in the first quadrant to start, then we go to quadrant 2, quadrant 3. Now we're back in quadrant 4. And the rule tells us to flip the coordinates. So 2, 3 becomes 3, 2. But then you want to negate, take the opposite sign on the new y value. So where we start is up here at 3. Then we're going to be negative on the y value where we end up. So there's a numerical example. If we start out 2, 3, what a 90, 180, and 270 degree rotation would look like. And you're going to be the same distance away from the origin with all of these points. So that's kind of the cool thing as you kind of make a circle as you rotate. So looking at the first example, we don't even need to graph it. That's the cool thing about this. When I see this quadrilateral, I want to rotate it 270. So that's telling me to look back to this rule. So R prime is going to then be, flip the order here on 3, 1. So it's going to be 1, 3. Then I need to negate the new y value. So it's going to be 1, -3. So if I start out in the first quadrant with this coordinate, I'm going to end up in the 4th quadrant after a 270 degree rotation, just like I did in this little example up here. It's going to take me around 270. All right, S prime, 5, 1 turns into 1, -5. T prime, 5, -3 turns into -3, -5. And U prime turns into -1, -2. So you're reversing the order on the x and y, and you're flipping the sign on the new y value. All right, pause the video here and try this triangle with a 90-degree rotation. Let's see what y'all come up with. All right, welcome back. 90 degrees says flip and then negate the new x value. But since it's a 0, you just kind of keep it as 0. K prime, flip and negate the new x value. And L prime, flip and negate the new x value. So 0 again, nothing doing there. And you can kind of think of this one, if you start out at 3, 0 and you rotate 90, you're going to end up 0, 3. And that's what happens with j to j prime. Whoop, there it is. All right, guys. The next paragraph gets us into the composition theorem that we learned back in 4.1, which just says if you do multiple things, you maintain an isometry. You don't change the size or shape. It's a rigid motion still. So when you perform a composition, you're just going to do a couple steps. All right? So we got to think back to the last section. First step here. Whoa, easy there. First step is to reflect in the y-axis. So I'm taking this segment. R starts out 1, -3. So therefore, R prime. Just change the sign on the x value. So that's -1, -3. And then S prime. Change the sign on the x value. So -2, -6. So there's our first movement. Next, we're going to rotate it, what we just learned, 90 degrees about the origin. So 90 degrees about the origin, I've got to go from where I ended up with the second step. Our double prime then tells me to reverse the order on those coordinates and then negate the new x value. So it's going to be +3, -1. So if you think about it, this point, -1, -3 would be in the third quadrant. Rotating at 90 should put me in the fourth quadrant, and it does, 3, -1. So it's kind of mentally keep track of what you're doing. Again, looking here at -2, -6, reverse the order and change the sign on your new x value. So that's a composition, friends. You're doing 2 steps in the same problem. All right, pause the video here and try this triangle composition after a rotation, then a reflection. All right, guys, welcome back. So first, I want to take a look at a 180. So T prime, 180 just says keep the order the same, just change the signs. U prime then would be -3, -5. And V prime would be -6 and -3. So starting out in the first quadrant, ending up in the third quadrant with the first movement. Next, from there, I want to reflect in the x-axis. So T double prime, a reflection in the x-axis just changes the sign on your y value. So -2 turns into +2. For U double prime, -5 turns into positive. And for V double prime, the -3 turns into a positive. All right, so we're just flipping up above now. So we were in the third quadrant, and flipping the x-axis is going to put us in the second quadrant. So -1, 2, -3, 5, and -6, 3, all in the second quadrant. So I like to do that, just kind of, think about what quadrant I start, what quadrant I end up when I make these movements, these transformations. So there you go. That is a composition. Woo! And our final objective today is to talk about rotational symmetry. So remember, typical symmetry is when we could cut a figure in half to fold it on top of itself exactly. Well, now you want to rotate a figure to map it onto itself exactly. Does that happen? So I start out with this fan-looking shape. Rotate it 45 degrees. We start to rotate counterclockwise. That's always the default in this book. And you want to go to 180 degrees or less. So, because if it has any symmetry before that, it's going to have it after that also. All right, so let's see here. As I turn this thing 45 degrees, it looks different. But when you turn it 90 degrees, that looks the same as how it started. So therefore, it has rotational symmetry at 90 degrees. Map it onto itself. 180 would also. So every multiple of it, as soon as you find one that works, any multiple of it is also going to work. So 180 will work as well. So this would have rotational symmetry at 90 and 180. All right, some examples. Starting with this parallelogram. Think about it like this. As you start to spin it, I'm rotating it. There's 90 degrees. It definitely does not look the same as when it started. But when you rotate it 180, it does. So therefore, this parallelogram would have rotational symmetry at 180 degrees. Regular octagon, start to rotate it. No. Yeah, good. It's going to have it there, and there, and there, and there. All of the times when it looks exactly as it did when it started. So how do you know when that is? Well, if we have a regular figure, all the sides are the same, all the angles are the same, you just simply take 360 and you divide it by how many you have. And that will tell you your smallest number. And then any multiple of that is going to work as well. So 45 works, and 90 is going to work, 135 is going to work, 180 is going to work. And you can stop there because rotational symmetry doesn't, you don't need to be redundant with it. It will do the same thing in the second half. So, it's kind of like putting 360. It's like, yeah, I know it's going to work, so you don't have to write. The trapezoid. Rotate, rotate, rotate. There's 90, nothing yet, nothing yet, nothing yet. 180, ooh, nothing yet, nothing yet, nothing yet. The only symmetry this would have is when you got all the way back to the start. So therefore, you'd have to say no on this one. All right, pause your video and try these last couple. All right, welcome back. The rhombus. Yes, indeed, 180 degree rotational symmetry. This octagon that's concave kind of has 4 points that are all the same. So therefore, divide 360 by 4. Every 90 degrees, that would work. Again, stopping at 180. And a right triangle, of course, would not have any rotational symmetry. All right, friends, so that's 4-3. Peace!